All right, beginning our next lesson here in our topic on proportionality and representations with proportional relationships. Looking at using similar triangles to describe a steepness of a line, kind of getting into what we'll learn later on about slope. So warm up here wants us to identify coefficients and constants in each equation. So a coefficient is just the term in front of a variable, would be the easiest way to describe it. So for number one, the coefficients, I'm just going to put CO for coefficients, would be 64. And a constant is just a regular old number. It's the easiest way to describe it. So the constant there would be 24. For the second one, the coefficient in that expression would be -8, and the constant would be 36. For number 3, we don't have any constants, but we have two coefficients here. We have -3 in front of that a squared, and then 18. And then for number 4, we got two coefficients again, 42 and 27, and then we have a constant that is -1. Okay, so key terms again, going to be looking at today, rate of change and slope. And you're going to recognize the connection between similar triangles and steepness of a line in order to determine those things. So on the getting started activity here, for each triangle, we're just going to write a ratio that represents the height and the base of the triangle. Because when we start talking about slope, we're going to be talking about rise over run. So the height, let me change to a different color there. Height to the base. So for the first one, we'd have 10 over 10. So that's for A. For B, we'd have 15 over 4. For C, we have 15 over 15. And then for figure D, we have 12 over 3. So if we wanted to write each ratio as a unit rate, essentially that means divide those. So for A, the unit rate there would be 1, 10 divided by 10. For B, the unit rate, 15 divided by 4, would give us 3.75. For C, 15 divided by 15 again would be 1. And for D, 12 divided by 3 would give us a unit rate of 4. So how can we use these rates to compare the steepness of the triangles? Well, we can see that A equals C. Those are both 1. And then D is steepest because it is the greatest ratio. So the larger the rate of change, the steeper that line is going to get. Okay, so moving on to activity 2.1 about constant proportionality and rate of change. It says on Monday, Jack and Jill walked from their home up a hill to get to the bus stop. They walked 4 yards every 3 seconds. So we could write an equation to represent that distance they walked over time. And we could say the distance is equal to 4 over 3, 4 yards every 3 seconds, times t, the number of seconds. Okay, wants to know, does this situation represent a proportional relationship? If so, identify the constant of proportionality. Yes, we have a proportional relationship, just like we talked about in the last lesson. Direct variation is proportional if we have a y-intercept of 0. So the constant of proportionality is 4 over 3. And we again know it's proportional because we have a y-intercept of 0. Goes through 0, 0. Goes through the origin. Okay, so if we wanted to complete this table, we know at 0 distance from home, they would have spent 0 seconds walking. And then we're going to be plugging in those x values, or t values, you could say, to our expression, d equals 4/3 t. So if I plug in 1 for time, I'm going to get 4/3 from my distance from my output. If I plug in 3 for time, 3 times 4/3 will give me 4. I'm going to skip down to the next two outputs, then we'll come back to the one where we're missing the time. So if we plug in 7.5 seconds, we're going to end up with 10 for our distance in yards from home. And then 9 seconds, 9 times 4 over 3 gives you 12. And then working backwards, if we go back to the one where we had distance is 8. In other words, if we said 8 equals 4/3 t, we would multiply by 3 over 4 to solve for t. And 8 times 3 is 24 divided by 4, and that gives us 6. So we end up with time is 6 for an 8-yard distance output. So if we wanted to graph that, I'm just going to graph the whole number points. I'm going to leave off the fractions. I got 0, 0, 3, 4, 6, 8. And that's enough points to draw our line. We can see our line here. And that line would represent that slope of a constant of proportionality of 4 over 3. I think I left off the 3 up here, I just noticed when I wrote that. So back up, notice, if you missed that up here, I'm going to circle it in blue. I left off the 3 on the denominator there, so it should be 4 over 3. Okay, so what is the unit rate? Well, the unit rate is 4 over 3. If we were to divide that, 4 divided by 3, 4 divided by 3, we should get 1.33. Okay, then we're going to look at explain why Tanner's reasoning is incorrect. Tanner says this graph goes up from left to right because Jack and Jill were walking up a hill. Well, the graph is going up from left to right, is increasing, but our y-axis is distance and our x-axis is time. The elevation of the hill has absolutely nothing to do with the situation. So he is incorrect because the hill is not a variable. It's not our input variable, it's not our output variable, so it does not have an effect on that situation. All right, on to the next page. So rate of change for a situation describes the amount that the dependent variable changes in comparison to the amount of the independent variable, also known as our slope in the situation. So consider Jack and Jill's situation. If we want to identify the independent and dependent variable, the independent variable, our x, was time in seconds. Okay, our dependent variable, the y, was distance in yards. So identify the rate of change. Well, the rate of change was 4 yards every 3 seconds. And it was increasing. So it says, consider the rate of change, the constant of proportionality, and the unit rate for this situation. What do you notice? Well, they're all the same. A, the constant proportionality, is the rate of change. They're all equal to 4 over 3. Okay, and then number 8 there, how would the rate of change and the graph of the relationship change if Jack and Jill walked faster? Well, if they walk faster, the rate of change is going to increase, and when the rate of change increases, the line will get steeper. So the line would become steeper. As rate of change would increase. All right, activity 2.2, looking again more specifically at slope. The graph shown represents the relationship between the time Jack and Jill and the distance they walked from their home. So let's analyze 3 different moments in time during Jack and Jill's walk. Time of 1 second, time of 3 seconds, and time of 6 seconds. The graph shows a right triangle at time of 1 second. I'm going to trace that here. Okay, it wants us to trace the triangle on a piece of patty paper. Now, we can't do that digitally here, so I'm going to draw the triangles and then label horizontal and vertical sides of the right triangle with respect to lengths. So, for instance, for at 1 second there, this side was 4, this side was 3. If I were to draw a right triangle for this next point and label the sides, I'm sorry, this was 4/3. It was counting by, not by ones. Let me fix that. Four-thirds over 1. There we go. All right, now fixed. So the next one, this is where we are 4 units vertically, if you look over at the y-axis, and 3 units horizontally, so 4 over 3. And if we look at the even bigger triangle, I draw one here in green. Vertically, we're at 8 units. Horizontally, 6 units. Okay, so we can see they are all the same ratio. If we're comparing 8 to 6, we do it in blue, 4 over 3. And the red one, 4/3 over 1. They all simplify down to be 4 over 3. Okay, so we drew the right triangle. All 3 of them was, like it says in number 2, modeled that. It says then trace each triangle on a separate each piece of patty paper. Again, I traced it all into 1, just using different colors. We labeled those sides. And 3 says determine the steepness of each triangle by writing a ratio. Well, we just did. So we got 8 over 6, 4 over 3, and 4/3. So those all simplify to be the same, which makes sense because they are all constant. It's a straight line. We have a constant of proportionality here. So how do these ratios compare? They are all equal. Okay, so what is the relationship among all of the right triangles? Well, they're all similar. They're all similar. They have equal angles and proportional but different side lengths. So that makes them similar figures. Okay, identify and label the triangle that represents the unit rate. That was that smallest triangle. Again, I'll just draw a little replica of it here. That was when we had 1 unit horizontally and the vertical change was 4/3. That represents our unit rate. Okay, and it said slide the unit rate along the graph of the line. What do you notice? All we would see if we slid that along it is that the unit rate is the same for the entire graph. So it's same for entire graph because it is constant. It is a linear function that is proportional. Okay, and 7, same thing. Slide the other 2. What do we notice? Same answer for there as well. Just emphasizing that that rate of change is constant across the entire length of that graph. Okay, it says in the last 2 activities, we investigated a relationship using a rate of change of 4 to 3 to represent Jack and Jill walking 4 yards away from their home in 3 seconds, or as a unit rate of 4/3 yards per second. Because this situation is proportional, the rate of change can specifically be called the constant of proportionality. And it's often, you'll see it represented with a K. So in this activity, we created 3 similar triangles, each using 2 points from the line to explore the steepness of the line and by sliding the similar triangles along the line. You noticed the steepness of the line remained constant between any 2 points of the line. In any linear relationship, slope describes the direction and steepness of a line and is usually represented with the variable m. Slope is another name for rate of change, and it represents the ratio of the change in vertical distance to the change in horizontal distance between any 2 points on the line. The slope of a line is a constant between any 2 points on the line. So the vertical distance over the horizontal distance. That's why we often will call it rise over run. how much we're going up and down versus how much we're going horizontally left and right. Okay, it says we wrote the equation D equals 4/3 t to represent the distance D Jack and Jill walk from their home with respect to time. So we're going to generalize this relationship on the next page. So it says let y represent the dependent variable, x represent the independent variable, and m represent slope of a line. So a general equation we could write for these quantities is y equals mx. Slope times your input variable to give you your output variable. How is this equation similar to the equation of constant of proportionality? Very similar. Slope means the same thing essentially as your constant of proportionality. It's just the change in y divided by change in x. Okay, slope can just be applied to situations that aren't proportional, which is the only difference between the constant of proportionality and slope. Slope can apply to other lines that don't necessarily start at the origin. So moving on to activity 2.3, equation for a line not through the origin. This is when we're looking more specifically at slope and not constant proportionality. It says Jack and Jill's Aunt Mary lives 10 yards from their home closer to the bus stop. So after spending Monday night in Aunt Mary's house, they leave for the bus stop there Tuesday morning, and they walk at the same rate from either house, 4 yards every 3 seconds. So the graph shows our original equation, y equals 4/3 x, representing that relationship between time Jack and Jill walk and their distance. So comparing the two situations, how do the slopes compare? The slopes will be the same. It's the same rate. The only difference is our new line is going to start at 10 because it's 10 yards closer, but it's still going to have that same rate of change of up 4, right 3. And we get a line, if I can get my point to go, right there. So we get a line that is same rate of change, same slope, but we have a different y-intercept. So how do the starting points compare? One is at 0, 0 at the origin, and the other is at 0, 10, starting 10 yards closer. So the line is shifted up. So I just graphed the line from the walk from their bus stop from their aunt's house. And again, if we had patty paper, if we're doing this in class, we could trace it and compare those slopes and discover that they are the same unit rate. And then it says translate the line to represent their walk from Aunt Mary's house and then transfer the line. So we already drew the line up there. The point now is looking at our equation change. So does your new line represent a proportional or non-proportional relationship? So this is the key between slope and constant of proportionality. This is non-proportional. Proportional has to go through 0, 0. So we can have a constant rate of change, but not be a proportional line because we do not have it going through the origin at 0, 0. So if we're going to fill in our table here, the new table, looking at the distance from their aunt's house. So we got a 0, 0, there's our original numbers, but now at 0, we're starting at 10 with our new line. So everything essentially is going to have 10 added to it. So you could say this would be 10 4/3, which is also equal to 11 1/3. I'm just writing 10 4/3 so we can see there's 10 added to it. So 10 added to 4 would be 14, then 18, then 20, and then 22. So how does this translation affect the unit rate? Unit rate is not changed. The line did not change steepness. So write an equation to represent the translated line. So all we're going to do is we have a y-intercept of 10 now. So our original equation was y equals 4/3 x, but now we have plus 10 on the end. So y-intercept has shifted up to 10. So it says we've written a general equation, y equals mx before, to relate the independent and dependent variables and the slope of a proportional linear relationship, how does this general equation change when the line is translated vertically b units? Well, the line changes by adding b to the end of it. So y equals mx plus b, which is the first form of a linear equation we'll learn, which is slope-intercept form. All right, next activity, 2.4, negative unit rate. Says Jack and Joe are walking back home from the bus stop, which is 30 yards from the house. They walk at the same rate, 4 yards every 3 seconds. So now we're considering these two graphs. So they're walking back to home, so the distance from home is getting shorter. So analyze the graph of Jack and Jill walking home from their bus stop. Does this situation represent proportional or non-proportional? Again, it's non-proportional. The y-intercept is not at 0, 0. So it is not proportional. Is the slope of the line positive or negative? Well, the slope of the new line, this one, is negative. It is a decreasing graph, so we have a negative slope. So if we want to compare and contrast those rate of change, again, we're going to skip past A. Class will take care of using patty paper to look at that. B, if we place the patty paper on the walking home from the bus stop, how can you transform that right triangle we drew from walking on the bus stop graph to the walking home from the bus stop graph? If we took that triangle and reflected it, if it was reflected, you would see that it is the same slope, but decreasing. So same slope, but decreasing. Essentially, if we had a triangle that looked like this, and we reflected it, we're now going to have a negative slope that's the same slope but decreasing. Okay, see, if we were to slide that triangle along those two lines, what would we notice? The unit rate is still constant. And what is the slope of the line walking home? So it's the same slope, 4/3, but it is now negative. Because it's still 4/3, so it's still constant, but it's decreasing, so it's negative. So if we were to write an equation for them walking home, they started 30 yards away. If we go back and look at that graph, starts at 30. So they have an equation of y equals negative 4/3. Oops, sorry, that all disappeared. Wonder if I can get it back. Nope. All right, so if you need to see that, just rewind and rewrite it. So y equals negative 4/3 x plus 30, because they started 30 yards away. And how does that equation we wrote represent Jack and Jill's walk home from the bus stop compared to the equation that represents their walk to the bus stop? Well, slopes are opposite. And they start 30 yards away from home. So they start 30 yards away. All right, activity 2.5, describing linear equations. So we've discovered that the equation y equals mx represents a proportional relationship. The equation represents every point x, y on the graph of the line with a slope of m that passes through the origin, 0, 0. Again, it's got to go through 0, 0 to be proportional. So an equation in the form y equals mx plus b, where b is not equal to 0, represents a non-proportional relationship. This equation represents every point x, y on the graph of a line with the slope m that passes through the point 0, b. So consider each graph. Determine whether the graph represents proportional or non-proportional. So if we're looking at A, this would be non-proportional. We're not going to write the equations. I'm just going to list if they're proportional or non-proportional, identifying them. If we look at B, this one would be proportional. Starts at 0, 0, straight line. If we look at C, this one again is non-proportional, because it does not go through 0, 0. And if we go to 2, it says determine the slope of this graph and write an equation to represent it. Describe the situation that could be modeled by this graph. So we got a horizontal line. Horizontal lines have a slope of 0. Your rise, if you talk about rise over run, is always 0. So 0 divided by anything is 0. And our equation would just be y equals 5. So a situation like this would be some input. No matter what we put in as an input, we would always have an output of 5. So example might be that my car is parked at a shopping mall 5 miles from my house. I'm not turning it on, I'm not moving anywhere. So no matter what, as the time passes throughout the day, it's remaining 5 miles away. So that would be a constant flat line with a horizontal slope of 0 with a never-changing output of 5. So complete the table of values to represent the linear relationship specified. So if we were going to write an equation that's proportional, we'd have to go through 0, and each y divided by x would have to be the same. So 12 divided by 2 is 6. So this would need to be 6 divided by 1 to be 6, 18 divided by 3 to be 6, and 24 divided by 4 to be 6. So that would be a proportional relationship. Non-proportional, we would not be going through 0, 0. So we could create a variety of tables here. I'm going to say 0, 2. So it's got a y-intercept of 2. And I'm going to say it's going up by 5. So 1, 7. And then 7 plus 5 is 12. 12 plus 5 would be 17. 17 plus 5, 22. So that would be a constant rate of change. It's got a slope, rate of change of 5, but it's not proportional because it doesn't go through 0, 0. Okay, and then lastly, if we wanted to draw two representations, graph two representations, a proportional one just needs to be a line going through 0, 0. So if I go through the point they're showing, and then a non-proportional would be any line not going through 0, 0, going through that point. So there would be an example of a non-proportional relationship.